Hi everybody. So in this video, I'm going to show you how we can solve geometrical problems using complex numbers. So we'll work through three examples, and if you want to work along with me, you can download a copy of this PDF from my website. I'll leave a link below. In our first example, we're given that an equilateral triangle has the center at the origin, and that this point is given as 1 and negative root 3. We need to find the coordinates of the other 2 points. So if we write the first point as a complex number, it comes from the origin, and we'll call this Z1. We know it has 1 on the real axis and negative root 3 on the imaginary. So in x plus iy form, Z1 will be 1 minus root 3i. So what we need to do is to write each of these points also as a complex number. If we say this is Z2, and this one is Z3. So to work out Z2 and Z3, we're going to use a special complex number called omega. And this is e to the power of 2 pi over n I. And I'll show you where this argument comes from. You can see that each of these complex numbers are equally rotated around 2 pi radians. They are 2 pi over 3, or 120 degrees. This is because it's an equilateral triangle. So for instance, if we had a square, then we'd have pi over 2. If we had a pentagon, it'd be 2 pi over 5. So omega, I introduced you to omega in the previous video when we looked at the nth roots of a complex number. So omega will be 2 pi over 3i. And to work out z2, all we need to do is to multiply z1, the first root, by omega. And this will rotate it by 2 pi over 3 radians. And then to work out z3, we multiply it by omega again. So z3 will be 1 minus root 3i multiplied by omega squared. Okay? And we can work out each of these on our calculators, but I need to enter omega in modulus argument form. So this will be cos 2 pi over 3 plus I sine of 2 pi over 3. So if we go to our calculators, we need to select complex form, and then we'll enter the cos of 2 pi over 3 plus I sine of 2 pi over 3. Now what I'm going to do to make this easier to calculate with, I'm going to store this as a variable. So if we execute that, and then choose variable, and I'll store it as variable A. So now all I need to do to work out Z2, we'll enter Z1, 1 minus root 3i, and then we'll multiply that by variable A. And that will give us the coordinates of Z2, 1 plus root 3i. And then if we go back and make this A squared, we'll get the coordinates for Z3. This is just negative 2. So if we go back to our eigendiagram, Z2 will have 1 on the real axis and positive root 3 on the imaginary, so 1 root 3. And Z3 will have negative 2 on the real and 0 on the imaginary. Okay? So these are the coordinates of Z1 and Z2. So it's all about finding omega. We can either use it in exponential form or modulus argument form. Let's try another example. So in example 2, we're given that the diagram shows a regular pentagon, And we need to work out the coordinates of the other 4 vertices in exponential form. So perhaps you want to give this question a go yourself. You can pause the video, and when you come back, we'll go through the solution. Okay, so welcome back if you had a go. So if we say that P, we've got Z1, and this is equal to 2, and at Q, we've got Z2, and we need to write each of these as complex numbers. So Z2 will be Z1 multiplied by omega. Z3 will be 2 multiplied by omega squared. Z4, I'll label these on a diagram. This will be Z1 multiplied by omega cubed. And then T, Z5, this will be 2 multiplied by omega to the power of 4. And omega will be e to the 2 pi over n. And you can see we've got 5 equally spaced complex numbers. So this will be 2 pi over 5i. And again, I'm going to enter this as modulus argument form. So we'll have cos 2 pi over 5 plus I sine of 2 pi over 5. And to make this easier to calculate with, we'll store it as variable b. So now all we need to do is 2 multiplied by that variable b, and we'll get the coordinates of q. But we need this in exponential form. So we can press format, and we'll choose polar coordinates. And then you can see we've got for Z2, this will be 2e to the 2 pi over 5i. And then for Z3, we want 2b squared. We'll go to format, we'll change it to polar coordinates. So Z3 will be 2e to the 4 pi I over 5. For Z4, we'll change the square to a cube, format and polar. And then we get 2e to the negative 4 pi over 5i. And then finally for Z5, we get 2e to the negative 2 pi I over 5. So in exponential form, these will be the coordinates of the other 4 vertices. Okay? If you wanted to convert them back to x plus iy form, then you could just go back to modulus argument and work out the cos and the sine of the arguments. Let's try one more question. In example 3, we're given the equilateral triangle whose centre is not at the origin, and we're given one vertex, this one here. Now we can't use omega because this only works when the centre is at the origin. But what we can do is we can translate each of these points by the vector -2 and -√3. And this will move this point 2 to the left and √3 down. So the centre of the triangle is now at the origin. And it will move this point 2 to the left and √3 down. So this will be moved to about here, 3 and √3. And with the centre now located at the origin, we can use omega to work out the translated coordinates of each of these 2 points. So if we say Z1 is this point, 3 plus I √3, Z2 will be Z1 multiplied by omega, and Z3 will be Z1 multiplied by omega squared. And omega will be e to the 2 pi over 3I. And do remember that we stored this in our calculators previously as variable a. So all we need to do, if we enter 3 plus root 3 I and multiply that by variable a, we'll get the complex number for Z2. And this will be negative 3 plus root 3I. If we go back, enter Z1, and now multiply that by a squared, we get the complex number negative 2 root 3I. So if we plot each of these on the eigen diagram as coordinate pairs, we'll have negative 3 root 3 and negative 2 root 3. That'll be down here. So to work out the original coordinates, we need to translate these back. This will be the opposite of this vector. So we'll add 2 to the real and positive root 3 to the imaginary. So we'll get negative 1 and 2 root 3. We'll apply the same to this point, and we'll get 2 minus root 3. So this is our equilateral triangle here, okay? And then for part B, find the area of this triangle. So if I sketch this out separately, we know the horizontal length goes from negative 1 to positive 5. So this will have a base of 6. And the vertical goes from 2 root 3 down to negative root 3. So this will be 3 root 3. So the area of our triangle will be 1/2 of a base multiplied by the perpendicular height. And this works out as 9 root 3 units squared. Okay? Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe. And you can download the full lesson and the PDF that accompanies this video from my website, mrmathematics.com. I'll leave a link below.